Hello, everyone. This is Group 21. I'm Soumya. We have Jimmy and Akash here. We are going to give you a brief intro to incentive mechanism design for unbiased federated learning with randomized client participation. So the core idea of this paper is designing incentive mechanism for federated learning. Federated learning is a distributed machine learning approach where you have a global model and you have a local model, and both of them work in sync to give you a better result. And our goal is to propose an unbiased federated learning model checkpoint somehow in this distributed mechanism. So in a nutshell, the goal of this paper is unbiased incentive mechanism, measure each client's contribution to global model performance, and design intrinsic value. So to know more about all of this approach, we should understand about full client participation and partial client participation. So full client participation is when all of the clients take part in the global training objective, and partial client participation is when a subset of clients participate in the global training objective. So with the existing solution, we always produced a fixed subset of client, and these clients are always the same throughout the entire time of the training. So what it can lead to is statistical heterogeneity, which means some clients' data might not be representative of the entire client population, right? So in that case, it could produce a biased model. And if one model checkpoint is biased for the global model, it could affect the entire client spectrum, so which is not ideal. So in that way, to solve the problem, we propose a novel approach where we have a new aggregation scheme which produces the unbiased model, takes into account system heterogeneity and statistical heterogeneity, and we model this entire optimization problem as two-state Stackelberg game. And also we take into account randomized client participation, and randomized client participation ensures that we don't have a fixed subset for the entire time of global training objective. So, and this has two parts, like one is from the server's viewpoint and the other one's from the client's viewpoint. So the paper introduces two novel concepts for client's viewpoint, that is local cost model and intrinsic value model. And from server's standpoint, they introduced randomized partial client participation and bidirectional payment. So local cost model and intrinsic value basically together quantifies a client's importance in the entire mechanism. The client may be getting a better model from the server. So in that sense, the client should do some transaction towards the global model or to the server. That is covered by the bidirectional payment, where in traditional approach, the server always paid the client for incentive mechanism, but now the client can also pay the server if the client has less data or low quality data, but it's getting a lot of benefits from the global model. Finally, we conclude with the results. The results clearly show that it outperforms the existing approach. So we have low loss and high accuracy with the proposed pricing scheme, and it yields higher total clients utility with system parameters proposed. And these are clients' intrinsic value, client local cost, and the budget. And also, it achieves unbiased, incentivized random client federated learning model, and the authors show that it almost approaches the global optimum. We can see from the diagram this claims about the results. The model has better accuracy with our proposed design. To conclude or summarize the entire paper, we can say that we proposed a new way for devices to join the federated learning that gets better results without bias. The second thing, we figured out how different device involvement and data affect the overall model. And then devices that contribute more get rewarded more, which is very common sense, and the paper covers that. Also, devices can choose to pay to help improve the model they care about, which is in the line with the intrinsic value model. So we have two comments about this paper, that the paper doesn't specifically mention what kind of machine learning algorithm they have evaluated on, so which is a very big talking point. And also, like, for this distributed systems in practical scenarios, you might have some security vulnerabilities if our new algorithm or the author's new algorithm introduces any new security vulnerabilities or not. They do not mention that. Also, they forgot to mention about the trade-offs, like maybe different clients' local model have different machine learning algorithms. That would be how we are supposed to manage that. So we conclude it here. Thank you for listening.